Excellent. So here we go. It's going to make this big, just so it's convenient. Right. So, in fact, I tried not to prepare for today's lecture because I wanted to give you a demo of how I would act in your shoes. If I were a little student having to read a new chapter in the book to prepare for class, how would I go about that? And how would I feel about all those kinds of emotions? I said we mentioned things. Look ahead and start. This last section is very important. We have to do this. It's about symbol tables. It's a data structure like the one we've seen, which are basically just arrays and linked lists and objects. Objects are data structures in themselves because they're fields that contain a lot of data. They form little data structures also. So we have objects which we used to call records. It's a collection of data, an object. Then we have arrays, and then we have linked lists. So symbol tables is another kind of data structure. It's also a collection where I can store a lot of stuff and take it out again, or just retrieve it, look at it. They're used all over the place, but it's a high-level data structure. So conceptually, it's much more advanced than just a linked list. What is the high level? What's the mathematical view of a linked list? What concept in mathematics have you studied that's like a linked list? Is a linked list like a function? You nodded. I saw that. It was a micro-expression. A microaggression expression. Is a linked list like a function? Yes. Okay, good. Do you put things into a function? The x's, I guess. Can you take them out again? Can you take the x's back out of the function? Or delete them from the function? No. Okay, right. So functions are not the model for linked lists. What other concepts have you learned in mathematics? Let's say that calculus is another name for one aspect of mathematics, and it's not really a concept. But that's on the right line. What did you learn in calculus? What are excursions? Excursions, yes. What did you? Well, okay, so the integral, that's a concept. The integral of a function, that's the area below the function. Is that like a linked list? Yeah, not really. Derivative. Oh man, we didn't do anything else in mathematics. Those were the three things we learned about: functions, derivatives, and integrals. What in? Matrices. Yeah, they're a little like an interest. You can put stuff in them, and you can kind of delete it if you put a zero in its place. That's not exactly the right model. It just doesn't feel right. So let's think of something else. Limits. What else do we do? What about something that you studied in grade 3? I hope so, because I studied in grade 3. No, I didn't do addition until much later. No, grade 3, we did sets. So we had little sets, and you could add little, it wasn't even symbols, it was just little squares and circles and shapes to the set. So is a linked list like a set? Well, it sounds good. You can add things to the set, you can take them out again, you can check if they're in the set. So a linked list is a set is a very nice model for a linked list. Set fails in one respect, and that is that in a linked list, in a stack, in a queue, in a collection, I can add the same item more than once. And if I add it twice to the stack, it's in the stack twice. And I can take it out twice. If I take it out once, I can check and it's still there. Because I've added it twice, I need to remove it twice to get rid of it altogether. The set is not like that. You know that all the elements in the set are unique. So that there are no repetitions in the set. So what other mathematical concept do you know that's like a set, but can contain multiplicities? That's the mathematical term. I happen to know it. You haven't learned that yet. Okay? So there's something called a bag. In mathematics, you have sets, contain unique elements, and you have bags, and multiplicities of a single element. So a bag is like a set, but it can have 2 A's or 2 X's or 3 X's or 5, however many. And that's exactly what a collection is. The mathematical model of a collection is a bag. Now, we have to talk about symbol tables. And you can't integrate them, you can't differentiate. But they're like discrete functions where the function maps some value, x value, to a different value. I could ask, what's the f of 20, and I'll get some value. And that's associated. And for every value I put in, I only have one mapping. Not all values are necessarily defined. It may be that I have a function that there is no x that maps to 17. So it's not all of these are defined, and it may not be that all x's are defined either. There are functions that are undefined at certain points. So the function 1 over x is undefined at the value 0. What is f of 0? There is no value. It's undefined. It's not infinite. It's not something funny. It's undefined. That's what we have. So we are going to have symbol tables, and they are going to be like functions. I want to associate one value with a different value. I want to check up. I want to look up. What is the value associated with my particular value? I want to remove some values. I want to say, previously I associated x with 20, but I no longer want to have that association. I can change associations. I can say x used to be associated with 20, but now it needs to change to 15. And what else can you do? So for some symbol tables, you can even do a reverse lookup, where you say which values are associated with 11. And I get all the x's that are associated with 11. And what is the other operation we need to have on symbol tables? This is all before I've started reading the book in my little simulation of what it's like to be a student. I'm just thinking out loud. Well, doing quite a lot of thinking for a student who's never read the chapter on symbol tables, but never mind that. What is the other operation that we'll probably need on symbol tables that we learned about on Monday? Iteration. Okay, we may want to walk through the whole symbol table and find all the mappings that are in the symbol table. Okay, right. So what does this stupid textbook say? Let's see. A symbol table is a data type. Yeah, we've just discussed that. That's fantastic. To associate values with keys. So little terminology. The x's, the things I associate with, are called keys. So f of a key is equal to a value. The ones in the other column, the y values in the function terms, are the values. So I can associate, well, it's difficult to put in words, but we'll see it in a second. Then, so Java has certain terminology, and this terminology is pretty widespread, and it's not universal. So we're going to read a few words that may not always be the same words for different languages. Java has, clients can store, Java calls that put. You can't see properly, so let's zoom. Why do I have a little rainbow every time I press a key? Am I still on air? Yes, beautiful. That must be so annoying, me checking if I'm on air the whole time, but never mind. There we go. So clients can put an entry into the symbol table. I can add another mapping. I can retrieve or get, is the Java term, the current value that a key is mapped to. For example, okay, so where do we use this? We use it all over the place. Many data structures in Java, in Java programs, in programs in other languages are implemented with symbol tables. In fact, the Java compiler itself uses a load of symbol tables. In fact, where the name comes from. The symbols that you use in your program needed to be stored in the table, and used to be called the symbol table, and now we use it all over the place. What else do they say? You want to look up a student's information, such as their addresses. What is It's upside down. Okay, good. You can come in. I just had to be sure, you know, it's a protest. Security's really tight. So, we associate student numbers, your student numbers are associated. You guys have to stop chatting. I'm dying of curiosity. What are you doing? Stop talking about. Daredevil. That's fine. I can't start, I mean, something's going on. I just can't tell what it is. Anyway, so we associate your student numbers with your name. We have a symbol table for your student number and a record, object instance, that represent you. Remember that the Stellenbosch University is not just a number. You have 8 numbers. So we have a symbol table that associates your student number with an instance of object that has all the info about you. Your name, your address, your marks, the courses you're taking. Your parents and all that. Great. Sometimes you want to associate your names that map to numbers. And every name is mapped, well, let me rephrase. Every number is mapped to one name. Is that true? See, I'm thinking about the fact that some people can have multiple telephone numbers, which is something we can't do with a simple table. If I associate Johnny with the telephone number 123, I can't associate Johnny with the telephone number 789 also. If this were a function, the function value of Johnny would be either 123 or 789. Can't have be both. Conversely, do all telephone numbers have a unique association? Well, some are undefined, but if they are defined, does one telephone number always belong to one person? Well, mostly kind of maybe. I mean, the university's telephone number could be answered by those people. Of course, they don't appear in the telephone book. That is something when we are writing either one telephone number only, or every telephone number has one name. If I want I've completely forgotten that they actually use more and stabbing, so binary search is one alternative, the other alternative to look at. It's remarkably simple. That performs well. It doesn't. We use hash table. It also implementation styles are quickly. Hash tables performance is order 1. It's constant time on average. Sometimes it's no longer, most of the time it's a lot quicker to classify. So, you think that's possible? So, yeah, it's in binary search trees are used in real life industrial applications, but I'm not sure if they're used for symbol tables, they're used for something else. The BSD code that we consider is only slightly more complicated than the linked list code. That is true. It's a little like linked lists, but I mean, you can imagine, instead of having one next pointer, you have two for your two children. I'm a binary tree, so I have two children. Right. So we'll get to all of that. We'll probably look at the API first. Yes, here we go. The API for a symbol table. And I said like 5 minutes. It's me like 3 minutes more. Let's just look at the API. So, once again, the book does not use an interface to specify this API. And if you think about last semester, we didn't use the interface either. We just wrote them down like this when we did see them, read them like this. But in this course, we've already learned about API interfaces, so I'll rewrite this interface in class on Friday. But let's see what it contains. Oh, well, firstly, it's a generic type. Aha, it's parameterized. So instead of having a symbol table that maps strings to numbers for a telephone book, I can say I want a symbol table that maps this kind of class to this kind of class. String double to string. Linked list to stack. I can have that. I can have a symbol table that associates with every linked list that I give it, it associates a stack. I can put anything in there. So here it says the keys and comma, the value. So it actually takes two kinds of types. Before we had a linked list, sorry, a stack of iterm. Iterm was the only type we didn't know. We could parameterize. But this time, we're adding a second type. Forget about all this stuff. I don't want you to see that. In fact, I should have made prepared a slide when it's not present. But a symbol table has two parameters. It takes in a key type, comma, a value type. And then there's a constructor that's empty. That's fine. It has a put operation where it takes two parameters, a key and a value, and it associates that value with that. So that's like saying number is 1, 2, 3. Then it has a get operation that takes only a key, Johnny, and sends back the value that is associated with Johnny. So if Johnny's in the telephone book, that value will be his telephone number, or it may be null if Johnny doesn't appear in the telephone book. And lastly, there's an operation called Boolean, which, called contains, which sends back a Boolean and also takes a key. And what we're asking is, does the symbol table contain an association for this key? Does Johnny appear in the symbol table? What is missing here, and what we'll add later on, is an iterator that will go through all the associations. Remove, that takes out an association. I put Johnny 1, 2, 3, and then the key that tries all. And then later, when I want to replace that association, I can say 7, 8, 9. And now the 1, 2, 3 is thrown away, and Johnny's association becomes 1, 2, 7, 8, 9. So implementation should also implement the iterable key to enable clients to access keys in sorted order for each loop. In sorted order, we'll be doing that. Yeah, okay, let's do it. So we'll add iterable, and it'll actually return all the entries in the telephone directory in sorted order, starting with all the A's, B's, and C's. So that's the API. We're going to start looking at the implementation on Friday at 8 o'clock. I'll be now. I want to record that.